Decode Ways. Imagine this: you're in a high-pressure tech interview, and you're handed one of the trickiest DP string problems out there, Decode Ways. This Pattern Mastery 100 staple isn't just a test of coding, but of true problem breakdown and logic. Did you know that over 40% of candidates get tripped up by edge cases with leading zeros or multi-digit decodings? If you can master Decode Ways, you'll be ready for any string or DP problem thrown your way. So let's crack it together. Here's the breakdown. You're given a string of digits, like 102,213, and each digit or pair of digits can map to a letter, 1 to A, 2 to B, 26 to Z. Your job? Count how many ways you can decode the string, following those rules. A 0 on its own is invalid, but 10 is valid since it maps to J. What are all the possible decoding paths? Now, let's assess the challenge. A brute force recursion would explore every way to split the string, but it's way too slow. We need dynamic programming. For each position in the string, we'll store how many ways we can decode up to there. Key edge cases? Zeros. 0 isn't a letter, but 10 is valid. We need to handle both single-digit and two-digit decodings. Here's how we'll structure it. Set up a DP array where dpi is the number of ways to decode the first I characters. Initialize dp0 equals 1, empty string is one way. For each position I from 1 to n. If si1 is valid, not 0, add dpi1. If si2:i is between 10 and 26, add dpi2. Let's try to implement it using solution 1. Time complexity is on. Space complexity is on. This solution uses recursion with memoization to count how many ways we can decode a digit string into letters. The key idea is that at any position I, we ask one question. How many valid decodings can I form starting from here? From that spot, we typically have up to two choices. We can decode one digit and move one step forward. Or we can decode two digits together and move two steps forward. But we only do that second option if the two-digit number forms a valid letter value from 1 to 26. Memoization stores the result for each index. That way we do not recompute the same suffix over and over. This turns what would be an exponential search into a clean linear time solution. First, we store the length of the string. Then we create a memo map. This memo remembers how many decoding ways exist starting from each index. So if we revisit the same index later, we can instantly reuse the answer. Now we define DFS at I. DFS at I means how many ways can I decode the substring starting at index I. Once we can answer that for every I, the full solution is simply DFS at 0. These rules keep the recursion correct. If we reach exactly the end, that means we successfully decoded everything. So that counts as one valid way. If we ever land on a 0 character, that path is invalid. No letter maps from 0. And if we are at the last character and it is not 0, there's exactly one way to decode that final single digit. Before exploring choices, we check the memo. If we already computed the number of decoding ways from this index, we return it immediately. This is what keeps the runtime fast. First, we try decoding just one digit at index I. If it is valid, we move forward one step. Then we count however many ways exist from there. Next, we try decoding two digits together. That can be something like 12 or 26. We convert the next two characters into a number. If that number is 26 or less, it represents a valid letter. In that case, we add the number of ways from two steps ahead. This is how we combine the two possible decoding paths. Once we have counted the total ways from index I, we store it in the memo. Then we return it. That way, if another path later needs the answer for the same index, we can reuse it instantly. Finally, we start decoding from index 0. And we return the total number of valid decoding ways. And that's how this algorithm works. It first sets up a memo map to cache decoding counts from each index. Then it recursively tries taking one digit or two digits when valid and sums those possibilities to get the total ways. Efficient, simple, and elegant. Test case check. Decode ways using recursion plus memo. Let's test our function using this input. 12. This string represents an encoded message where each digit or pair of digits maps to a letter. 1A, 2B, 26Z. Here's why the solution works. We use recursion to explore every valid way to decode the string. First, we try decoding one digit at a time. Then, if the next two digits form a valid number between 1 and 26, we explore decoding them as a pair as well. Memoization ensures we don't recompute results for the same index more than once. And that's exactly what our program outputs, too. This confirms that the recursive plus memoized approach is working correctly and matches the expected result. Wrap up. So, our implementation is correct. The algorithm successfully counts all valid decoding paths by exploring single-digit and double-digit options, efficient, accurate, and reliable. Let's try to implement it using solution 2. Time complexity is O(n). Space complexity is O(n). This solution uses bottom-up dynamic programming. That means we compute answers for smaller suffixes of the string first. Then we use them to build the answer for the full string. We create a DP array where DP at I means one thing. How many ways can we decode the substring starting at index I? Starting from the end is convenient. Decoding decisions at I depend on what happens at I plus 1 when we take one digit. And they depend on what happens at I plus 2 when we take two digits. We also handle a key rule. Any segment that starts with the character 0 is invalid. So it contributes 0 ways. First, we handle the edge case. If the string is empty, there is nothing to decode. So we return 0. Then we create a DP array of size n plus 1. Each DP at I will store the number of decoding ways from index I onward. Now we set up the base cases. DP at n equals 1. That means there is exactly one way to decode an empty suffix. It means we have successfully finished decoding. For the last character, we check if it is 0. If it is 0, it cannot be decoded alone. So DP at n-1 becomes 0. Otherwise it is a valid single digit. So DP at n-1 becomes 1. Next, we fill the table from right to left. This direction is important. Each position I depends on already computed values to the right. Those values are DP at I plus 1 and DP at I plus 2. If the current character is 0, we cannot start a decoding segment here. So there are 0 valid ways from this index. We set DP at I to 0. And we move on. If it is not 0, we have at least one valid move. We can decode one digit. That contributes DP at I plus 1 ways. Then we also check the two-digit number formed by the next two characters. If that number is 26 or less, it is a valid letter too. So we add DP at I plus 2. Together, these represent all valid decoding paths starting at index I. After the table is fully built, DP at 0 contains the number of ways to decode the entire string from the start. So we return DP at 0. And that's how this algorithm works. It first sets up a DP table with base cases for the empty suffix and last character. Then it fills the table from right to left by adding one-digit decodes and valid two-digit decodes to compute the total ways. Efficient, simple, and elegant. Test case check. Decode ways using bottom-up dynamic programming. Let's test our function using this input. 226. This string represents an encoded message, where each digit or pair of digits corresponds to a letter from 1A through 26Z. Here's why the solution works. We fill a DP array from right to left, where DPI represents the number of ways to decode the substring starting at index I. If the current digit is 0, it contributes 0 decodings. Otherwise, we add DPI plus 1, decoding the current digit alone, DPI plus 2, decoding the current two digits together if they form a number less than or equal to 26. And that's exactly what our program outputs. 3. This confirms that our bottom-up DP approach is computing the decoding count correctly. Wrap up. So, our implementation is correct. The algorithm successfully counts all valid decoding paths using an efficient DP table, reliable, accurate, and performant. Decode ways. Let's do a recap. So, how do you turn a string of numbers into letters, and how many ways can you do it? Decode ways is one of those deceptively simple dynamic programming problems that really tests your logic under pressure. Once you understand its structure, though, it becomes one of the most elegant DP challenges out there. Breakdown recap. We started by understanding the core problem. Given a string of digits, each single or double-digit number can represent a letter from A to Z. The goal is to count how many valid ways you can decode the entire string. But there's a catch: zeros can't stand alone, which makes handling combinations like 10 or 20 critical to getting the logic right. Assess recap. We compared the brute force recursion with dynamic programming. Recursion explores every possible split but grows exponentially. DP, on the other hand, builds the solution step by step by remembering how many ways we can decode each prefix. That's the key to handling overlapping subproblems efficiently. Structure recap. Our plan was clear. We used a DP array where each position represents the number of ways to decode up to that point. For each digit, if it's valid, not 0, we carry forward previous counts. If the last two digits form a valid pair between 10 and 26, we add in the count from 2 steps back. By the end, the final value tells us the total decoding count. Implement recap. We implemented this logic in Python and ran it on LeetCode without any errors. The DP solution worked efficiently in ON time and space, and we even noted that it could be optimized to O1 by using just two variables. Check recap. After running our test cases, The output matched perfectly with expectations. The DP table captured every valid decoding path, confirming that the logic worked for both regular digits and tricky zero cases. Closing insight. The big takeaway? Decode Ways teaches the heart of dynamic programming, breaking big problems into smaller overlapping parts. Once you master that pattern, you'll recognize it everywhere, from strings to sequences to any problem that builds on past results.